final two easy questions for Chapter 4 of Statistical Rethinking, second edition. So 4E4 is, in the model definition below, which line is the linear model? Okay, and so this is so that's a little bit confusing sometimes, I think, like to say that this thing is the model, and then to ask which is the linear model. So the linear model is, or a linear model can be part of the larger model, which contains, all of your prior distributions and everything. So anyway, we want to know which of these lines is describing or defining the linear model. Well, what's a linear model? If you're not familiar with what a linear model means, you might default to believing that it is something that defines a line, right? And so you've probably, you probably remember one of the equations for a line, which is y equals mx plus b, or something like that, where y is the value on the y-axis, x is the value on the x-axis, m is the slope, right? So for every notch in x, you go up by a certain amount, and you're offset somewhere by an intercept, and they call it b, or I learned it as b, but and you might just pattern match, and you might see that the second line here is the only one that is an equation, but it also seems to pattern match the equation of a line. But instead of b, we have this single term alpha, and instead of mx, we have beta x. And in this case, that would give you the right answer. But more generally, a linear model is going to be a model in which all of the terms, so I'll call this a term and this a term, all of the terms that contain a parameter, again, that's something that is not data, it's something that we're trying to estimate, can be written as either scalars, and so a scalar in this case would be the alpha, or a product with data, right? So here is beta, and it is being multiplied by x, right? And it's important that beta be multiplied by something that we have already observed, x in this case. So in other words, what a linear model would not include, not that these models cannot be dealt with Bayesian statistics, but a linear model would not include terms where the parameters are multiplied together in some way, right? So we couldn't have alpha times beta, or we couldn't have a beta squared term or an alpha squared term or cubed term or whatever, and we couldn't raise one parameter to another parameter. And you know what, there's actually another one. I'm going to pause it real fast to include this. Okay, and we're back. So anyway, with the linear model, the parameters can't be multiplied together, right? So again, so we can't have parameters somehow being multiplied together, and the parameter can't be a part of some power term like beta to the x or x to the beta or something like that, okay? So this more general definition will open up much more complicated models, linear models, where we might have multiple intercepts or multiple beta terms, and beta usually denotes the slope, like m denotes the slope, right? We might get multiple slopes. In other words, we might see that multiple predictive variables, x1, x2, x3, etc., affect the outcome y all independently. Okay. So again, for 4E4, the correct answer is the second line here. And now 4E5, in the model definition above here in 4E4, how many parameters are in the posterior distribution? Okay. Well, just like in 4E2 in the video before this, the number of parameters in our posterior is going to be the number of parameters that is not defined by other parameters. Okay. So up here we see that we have several parameters. We have mu, alpha, beta, sigma, but mu is being defined in terms of other things. Okay. So our posterior will not estimate directly a term for a posterior distribution for mu. We can't. It implies it because we will get posterior distributions for alpha and beta, and we already know x. X is the part of the data that we observed. And so we'll be able to infer a posterior distribution from mu, but our model will not kick out a posterior distribution for mu. So for 4E5, we have 3 parameters that are going to be in the posterior: alpha, beta, sigma.